Okay, so now step 3 is finding the time evolution of psi1, of psi I. Step 3, no, finding the time evolution of psi I of x. Okay, so this is basically psi I of x of t, which is, I think we are calling it just psi. And that is going to be given by, well, we know how to do this. Integral over d of k1, a of k1, psi of k1 of x, and now multiplying this by e to the power minus I by h bar, the energy, which is a function of k1 t. Okay? So here we know what the expression of a of k1 is. Let's put that in. So we have, here we have that. We did that by doing the Gaussian integral here. This was a Gaussian, and we multiplied it by that. So we get square root of pi by square root of, sorry, delta by square root of pi. And then we have, hang on, okay, so we have d of k1, and then we have e to the power, yeah, okay, yeah, e to the power, sorry, just, yeah, okay, yeah, oh, sorry, yeah. Now, this is something I'm not going to show, but, you know, we are free to choose the normalization, and the normalization that works is going to be a is 1 over square root of 2 pi. Okay, and okay, this is a, okay, yeah. Let me see if I can make another comment about this. Right, yeah. Yeah, because if you remember, what we did is that we set d equals to 0, and that had to do with the fact that on the right side of the step potential, we don't expect a wave going to the left. So that, and then we had leftover A, B, and C. And we expressed B and C in terms of A. Okay, so B and C was some function of K's times A, and C was some other function of A. So A can be chosen arbitrarily because the overall normalization is something that is up to us. And therefore, we are allowed to choose A to be 1 over square root of 2 pi. But that means that we don't have any freedom in choosing B and C. Okay? So let's do that. And if I do that, then this expression that I was trying to write, let me write that down below. Copy. Okay. So now what we're going to do is we have delta by square root of pi, the whole thing under square root, 1 over square root of 2 pi, and then integral over dk1, and then we have e to the power minus I h bar k1 squared divided by 2mt, right? So this is basically this guy. What we have done is that we have just written the expression for E explicitly, okay? And then let's write A of K1. So we just saw what A of K1 was. It had E to the power minus a Gaussian factor, K minus K, sorry, K1 minus K naught squared, del squared divided by 2. This was the Gaussian and momentum space. And then we had a phase factor, I of K1 of A. So this basically gets, deals, you know, so we have written this one and this one, and now we have to write this. And we did this before, so this has 3 terms, e to the power I, K1x, and theta of minus x, and there is b over a, remember the coefficient, then e to the power minus I, K1x, theta of minus x, plus c over a, e to the power I, K2x, but K2 is K1 squared minus 2m v naught divided by h bar squared and the whole thing in square root of x, and then we have multiplied d of x, and then we can close the bracket, and this gives us the expression for psi I at a future time t. Okay, so this is the formal expression. We now have to simplify it. Any questions about it? Okay, so let's consider the first term. So the first term, if I look at it, you know, there is an exponential, you know, the phase factor, which is K1 dependent, and there's another phase factor, which is K1 dependent. And, you know, so they will, they will combine together to make a phase K1 dependent phase factor. And here we see that there is K1 squared, and there's K1 squared. So in the end, you know, all these guys will combine to make a complex Gaussian. Okay? Now, I might show it, but you know, I want to probably leave it as an exercise. You can show that if you do the integration for the first after the first term, and it's a Gaussian integral, so it's not a difficult integral. What is difficult about it is to massage the terms afterwards. Okay, so and that's something that is one has to do. Maybe I will, if I have the time today, I will do this. Okay, the first term is a Gaussian. So Gaussian should be with a capital G. Is a Gaussian. Okay, let me just leave this as an appendix. So after the lecture, I will show you. The first term is a Gaussian, which after integration becomes. So what is the first term? Let us revisit it. It's the energy, time-dependent energy factor, which is which is a function of k squared, k1 squared. The Gaussian factor, which is also a function of k squared, and the phase factor. So if I combine all these exponential, it should be clear that it's a generalized complex Gaussian. Okay? Is that clear?
Yeah.
Yeah, makes sense.
Okay. All right. So, and we're doing the integral over K1. So we can, factor out this theta. So this theta doesn't matter. So after integration, this Gaussian becomes, and this expression is harder to show, but this is something we will show, is it becomes theta minus x. This is of course factored out. And then we have a pi to the power minus 1/4. And then there is a time-dependent normalization factor, which is delta plus I h t over m by 1 over square root of 2. You will recognize this as something from the assignment 2, right? And then we have the Gaussian exponential, which is minus x plus a minus h bar k naught t over m whole squared divided by 2 delta squared 1 plus I h bar t divided by m delta squared exponential ends. So this is the Gaussian factor. And then there is a phase factor, which is I k naught x plus a minus h bar k naught t over 2m. Okay, and we want to write this as theta minus x, so this is separated, as a Gaussian G, which is centered at, okay, let me just write it first, minus a k0t. So this guy is a Gaussian centered at x equals to minus of this guy, right? X equals to minus a plus h bar k naught t right, okay? This is what it is. So with time t, it's going to change, right? So as time t goes to infinity, what happens is that, this factor becomes a positive factor, right? So as t goes to infinity, this Gaussians, as t goes to infinity, this Gaussians overlap with, with the theta minus x factor goes to 0, right? So as t goes to infinity, this term goes to 0. Okay? Now this term goes to 0. Okay? Is that clear? Okay, so this term was the incident term, right? This was the incident wave factor, this was the incident wave, right? So this means that as t goes to infinity at large time, the initial wave packet vanishes. Well, that's exactly what we expected, because we would expect the initial wave packet to become separated into a reflected wave packet and a transmitted wave packet, right? So as time goes to infinity, the initial wave packet vanishes. Okay, any question about that?